All right, the first thing we're going to look at today, there's a couple of MATLAB scripts in the module section for, I think, last week, actually. And I meant to get to them before, but I never had the chance. I just want to run through them really quickly to show you just how you run it, and then how you change stuff to take a look at what's happening in these things. This one is completely optional if you want to use it. Yes, we can enable that. I think the recording's on. So, but it's just a demonstration or just to essentially fool around with the radon transform, which is what we looked at last week. We're going to continue it today. But you can look at the radon transform for a couple of example functions, and you can make your own function, read in your own function and do a radon transform of that. But one is a central square. There's one that's a set of small squares at different places in the field of view. Another image is the Shep-Logan phantom, and another one is a coronary image. This is an actual CT image. Okay, so it's a true functional clinical image. Okay, and you can just choose which one of these you're going to use by setting it to 1 and set the rest to 0, and then as you come through the code, it will create that image. This is the first thing it does. It'll just go down through here, and then it reads in the actual, if you've chosen this one, the coronary CTA, it'll actually read in that picture and create a data array from that picture. And then it just does a couple of very simple steps. And for all of these demo things that are just playing around like a little script on a Mac anyway, I don't know how you do this on a PC, but you click inside the code here. All the code is lit up. It's active. And if you hit Command Return, it'll just run the whole darn thing. Okay. And the first thing it does at the top is clear all the variables and close all the figures. So it just reruns the whole darn thing. And you can look at the windows that it's created. I give them titles so that we can just pick a window and take a look what we've got. So in this case, figure 1, we've got our original image. It looks like we picked a square that's a 16 by 16 square. It was that first option up there. Then look at the Fourier transform of our original image. This is what that thing is in Fourier space, at least plotted as the absolute or the magnitude of the Fourier coefficients, not the phases right now. And it's also the log of the magnitude, and you offset it from 0 such that you don't get weird behavior. And so if I look at, say, a row of this image and ask, what's the Fourier transform of that function, right? When I go down here and look at the Fourier transform across that, it is a sinc function, right? So it's this sinc thing, which you can see here has a peak, and then these side lobes go out like that. The position of these zeros, if this was if we plotted the real component, these would go negative and positive, negative and positive. The position of these zeros is obviously inversely proportional to the width of that rectangle. So if it was really wide, the position of those zeros would come in closer. If it's a really narrow rectangle, those zeros move out. So then let's take a look at, I plot up the parameters of the run because these are things you can adjust to take a look at what adjusting them means for CT scanning. And so it's the delta theta is the difference between or the theta steps between views when you take the raw data as projections. And then the angles that you're going to look at are 0 through 180 degrees in this example. You can change that. This is GL theta, which is the function that we were looking at for 2 lectures probably, is these are the projections, and you have the projection angle along here. There's 360 in this case, and then this is the L direction along here. Okay, so for a square like this, you can see that at 0 degrees, which is probably the vertical direction, you get a very uniform function, right, as a function of L, because every integral through that thing is the same wherever it exists. right? So if I'm integrating projections down this way, they're all going to be the same, except where they're 0. And then if we look at 45 degrees, we're going to get a peak right here, right? And that's when we hit the diagonal, that's going to be the maximum integral that we can achieve, so that our raw data will have a peak there. And then as we rotate, it'll go back to a very uniform or a rectangle function, right? So any questions about that? That's GL theta. We're going to continue on with our just, discussing this whole process. Let's see what else we've done here. A noise-free iRadon. So if I take this and I feed it back into the inverse radon transform in MATLAB, this is what comes out. So it should be this, right? Because they're inverses of each other. So if this has high fidelity and I take the inverse radon transform, I should get back to my original image. Okay. We can see if we want to check and see what happens if something goes wrong with the data. A way of doing that is just take your image, like this is your test pattern, get GL theta, and then say, what happens if my scanner, if the X-ray intensity changed as a function of time? Well, I can change GL theta to model that change, take the inverse radon transform and see what does that image look like under those circumstances, right? What artifact would appear under those circumstances? So that's a noise-free. Here's GL theta, this figure here, missing projections. Okay, so I've just said, well, I lost these somewhere along the way. So now I have a very finite, looks like 90 degrees worth of projections, or maybe, yeah, something like, 90 degrees worth of projections here. So what happens when I reconstruct that with just iRadon, assuming that this data, I'm making the assumption the data is good, use iRadon, what comes out? Does it look anything like my object? And it's this thing, right? So this is what iRadon produce, the inverse radon transform produces. So this is basically, as we saw last week, at the end of last week, this is the convolution back projection result of inverting this data when you're missing these data out here, and it looks like this. Okay, so the way you can use these simulations just to fool around, right, and see what's going on. So here we said 180. So let's see what happens if we say, you know what, we'll take a projection every 4 degrees. Just run the whole thing again and see what happens. Okay. So now my raw data, I've taken my GL theta, I have only out to, I only have 45 projections, I guess. And I've sort of, I've gone to 0 to 180, but in 4 degree steps. Okay, so these projections are much farther apart now. You ask, well, what does the object look like? It actually is a pretty good representation of the object, but we have all of these streaks out here, right? So that's the type of artifact that's going to get generated when we undersample by taking data, with big gaps. And let's see what else we can change. Let's go to an extreme. We'll say like we're going to do it every 8 degrees or something. And the artifacts start moving in and becoming a greater component of the image, but still not bad. If all you needed to know was the value of that square, like the mean value of the intensity of that square, this is probably just a fine way to do it, right? You don't really care about all these streaks and everything. Okay, let's see what else we want to change here. Let's go back to 1. And I know, let's do this. Let's change our image. If we go up, oh, that's an if. It's here. 0. What do you want to see? Want to see Shep Logan first? Let's take a look at what that looks like. So this is the Shep-Logan phantom. It's an entirely mathematical phantom. It's all of these shapes are ellipses. So you can write down the equation for these shapes. And in fact, you can write down the equation for GL theta. If you know these shapes analytically, you have an analytical expression for GL theta. You don't actually need to do a simulation. For most objects in the world, deriving the analytical expression for this is quite difficult, right? And it'll be an impossibly large formula. So most of the time you do a simulation. But here's the Fourier transform of that thing. It's much, more complex kind of thing. And here's what if we cut out some of the views, obviously we get a highly artifacted image. And then we can look at our clinical. I hope I've got the data in there. Looks like I do. Okay. So this is a coronary angiogram, one slice of a CT. This is the left atrium, the aorta. These little dots here are the coronary vessels running through this plane, right? And they're the things that you need to resolve usually very accurately to determine if a person has disease. And here's the radon transform of this, right? So this is GL theta again, and there's the inverse transform here. So it's sort of one-to-one map between this stuff and the image, right? Again, here's the artifact. So you can fool around with this as much as you want. Now let me see if I have an. Oh, this is it here. Let's look at this one. So this is of interest to you because it's on the homework. This is the one you download for the homework, and the images become a lot simpler. In this one, again, you can just run the whole thing because you've got to clear and close. Closes all the figures, clears all the variables, just does it again. And here's the original image, okay? And the original image is exceedingly simple. In MATLAB, to go in and look, you just hit zoom here and you can draw a little rectangle. Oops, should be able to. A little rectangle around that and see what it is in terms of pixels. So we've got this, inverse. Oh, this is the inverse radon of the noise-free image. So this is actually figure 4. So let's take a look at figure 1, which is the original image. Okay. And if I zoom in on one of those, it's just 1 pixel, right? So this is like a delta function, right? And then when I went and looked at my original data, so here's the parameters of the run. Delta theta is 1 degree, 0 through 180, signal to noise. Okay. I can look at my original GL theta data right here. It's very revealing about CT, right? So this is what raw data looks like for 1, 2, 3, 4, 5, 6 dots in the field of view, right? So it's pretty interesting, right? I mean, just in terms of learning what CT is actually doing, is that each dot traces out one of these sinusoids, right, in the GL theta space, right? And then they're all summed on top of each other, right? So that's what your raw data basically is. And now you take the inverse Fourier or inverse radon transform of this, right, to get back. Oops, my bad, sorry. Here. And you get this function. So it spread it out just a little bit, right? It's no longer just a single dot. It's got some wings on it, a little bit of blurring. And then for this one, we're going to look at what happens when you change the convolution filter. So in the convolution back projection process, as we saw last time, we convolved, our raw GL theta with the inverse Fourier transform of that ramp function. Well, you can change that to change the appearance of your image, that ramp function. And so we'll take a look at that today. The other thing that can happen is you can have noise on your raw data. And the noise comes from, just electronic noise in the system and natural variability of number of photons that you would imagine detecting. You're not going to get exactly the same number every time you do that measurement, right? And so there'll be variation. You can just model this as, say, a Gaussian distribution around some mean with random numbers that you would add to your raw data as a function of position. And so here's GL theta. This is the ideal GL theta. This is the GL theta with the scaled noise on it, right? So now we're saying we're going to model our noisy scanner by just putting noise on top of this GL theta, and let's see what happens to the image. And we can go back, and here's the iRadon with both a filtration done to reduce this noise level and the noise itself. So we're going to see some noise. So now remember what our first image, this was our starting image here. Oh, here, like these little dots, and this is what we get from this simulation. And what causes this blurring and change in signal to noise, etc., you can sort of discover through iterative running of this function. So we can go down here. Here's the data peak to noise ratio. So in our raw data, we look at all of the raw data in GL theta, find the peak, and then we set the noise level such that this ratio is achieved between that peak and the noise level. And for this example, I set it to 10. Let's set it to 1, see what that looks like. If we had really noisy data, right? The peak and the noise are about the same. That's what our picture looks like, right? If your raw data had a signal to noise of 1, right? And so you can start to see some interesting correlations in the reconstruction here. And this is due to the smoothing that we're trying to do in the raw data space to keep our signal to noise of the image okay. Right? So that's signal to noise of 1. What else can we change here? Adjustable recon filter. So you can put in a Hamming filter if you want, but I thought I wrote an actual, oh, here it is. And it's on. So you can actually smooth the data, and this is a trivial filter, right? This is convolving the raw data with a 3x3 box. So each pixel is actually just the uniform average of all of the pixels around it and itself, okay? So that's that. It's a square, right, that averages those. If we take the smoothing filter off, let's just take it off. Smoothing. Zero. Take that off. Let's try that. So now our noise is not smoothed at all, right? In the raw, because we're doing the smoothing in the raw data space, the GL theta space. And here's our picture. So we get a higher background noise level, but it certainly keeps the spatial resolution of the dots like tighter, right? So we can do that again. So this is with no smoothing, but our signal to noise is pretty low. I mean, remember we saw these sine waves here. Let's look at our theoretical GL theta is still that, right? But now the signal to noise is low. So when you put the noise in, it looks like this. And then when you take the inverse radon of that, right, it looks like this. So we still have, it's interesting, like when you look at this data, if you were to tell me you can see, 6 unique sinusoids in that data, it's kind of hard to see them, right? They're not that visible, right? I don't know what your screen looks like, but yeah, on your screen, they're invisible, right? However, there's a correlation that exists in that data along those sinusoids, and that shows up as this dot, right? Which is pretty impressive. So it's hard when you're trying to manipulate CT raw data in the projection space, because a lot of the things that you're trying to manipulate are very difficult to observe in the projection space. So often what you can do is do your first image reconstruction and then find areas or objects that you're interested in, and you go back into the raw data and pay attention to those spots and try and you know, do some kind of least squares estimate or some kind of noise reduction so that you bring out those objects. Right? So, okay, let's see what else we have here. The other thing you can try is smooth in different directions, right? So, like if we say we do this, say we do 3, 1 over 3, got to keep it normalized. So now we're just going to smooth in one direction, leave everything else the same in the other direction in the GL theta space. Let's see what happens there. That looks pretty good, right? So that was smoothing in the row direction. So that's up and down in MATLAB. Remember, it's a little confusing in MATLAB. This is our first coordinate, right? Because it's a row of the data. So we've smoothed up and down here. And that seems to have done a pretty good job. There's correlations obviously in the background noise, but the signal to noise of the dots looks pretty good. Let's try smoothing in the opposite direction only, or the orthogonal direction, not opposite. Okay, now we're smoothing this way, and it has created that kind of swirling background noise change, and the objects obviously change as a function of theta. If you want to take a closer look at this picture and you don't, like you need to do a center and window here, you can select it, go back here in here and go in contrast. Oops, my bad. Did I type that into my code? Okay, and it'll bring this up. And you can type in your width and your center. So here, if we want to go farther down towards the base, you say 0.1 maybe, and maybe make this 0.3. So that makes it sort of a higher contrast here. And now you can see some more details of this. So interesting, filtering in that orthogonal direction, right, had a completely different effect on our picture here, right, on the resulting image, in the sense that we start getting these correlations in this direction, right, as we move away from the center. So filtering in the raw data space is worth understanding. What else can we do here? Okay, that's about it. So, you know, you can mess around with that code, and the way, just change variables, hit go, and replot everything, and put up your own figures and your own plots and stuff that you want to look at. Okay, any questions on that? Okay, so we'll start where we were. Yeah. Oh, for the project, that's a great question. I think the TAs set up a billboard or a sheet, right? Google Sheet to get your teams together. How are we going to assign the date? Well, we're going to do it randomly, I think, right? So we'll just throw dice or something, pull out group numbers, right? And then, you know, tell you what the date is. Shouldn't make a lot of difference, because the people that are going to present live will either be on Halloween or 2 days after Halloween, right? And then the other folks, we want you to lay it down on tape or whatever at about the same time, and then we'll review it later. Okay, so everyone's going to have about the same amount of time to get that thing done. But we'd kind of like to get the Google Sheet done by today, right? would be the idea. Is everyone, or is somebody still looking for a group? Yeah. So I would okay, so everybody's in a group now. Thank you. Okay, so we're good. And then I guess at the end of today, right, we can just run a little shuffle, a random shuffle, and then pick the groups that are going to present when. We'll have to look at the topics and make sure like there's not 18, or, you know, I think, did you guys limit it to 3, max 3 per topic or something? That would have been probably ideal, but we'll see how it shakes out. But if we watch the same one back to back to back to back, that can get challenging. So we'll figure out something sensible. Okay, so it'll be random unless it produces something nonsensical, and then we'll change it, you know, with a tweak. Okay, so let's go back to where we left off on Wednesday. And so recall from the projection slice theorem, let's turn this off, sorry, that GL theta, you know, so this is the L direction, theta is the angle of the projection, and that projection, if you take the one-dimensional Fourier transform of that projection with respect to L, it gives you a sample through the Fourier transform of your original image at that angle, right, and radially through the origin. Okay, that's called the projection slice theorem. And analytically, so here's the God-given Fourier transform of our image that we're trying to reconstruct. And remember, our image is the mu value, or the attenuation coefficient at each point inside the patient. And the Fourier transform of this function is here in spatial frequency space. It turns out we sample this thing when we do those projections with this radial technique. And so we get this set of radial samples through this function. To take the inverse Fourier transform of this thing to get mu x, y, we need to because our data is in polar coordinates, we transform the Fourier transform into polar coordinates to do that. And that involves a Jacobian for each, you know, elemental area, because the size of an elemental area is obviously proportional to k as you're going out for each d theta and, you know, dk here. So this is the transformation of the inverse Fourier transform into polar coordinates using these equations here. And so now we have this here, right? We're going to parameterize this term with the single variable L, which represents the theta dependence, because these, remember, in the integral, these guys are fixed, x and y, because they're where we're going with this thing. So these are fixed. So this L is the parameterization of the theta dependence for this function. And we can look at the inside of this guy here, right? So this is a two-dimensional integral, but if we do this one first, where everything's dependent on k, we can call the result of this function GL theta, right? Theta is a parameter. It doesn't change, right? Because the theta integral is on the outside of it. And we wind up back in the spatial dimension with our variable L, because here we have spatial frequency. And so that's the inverse Fourier transform of this thing, gives us this function we're calling G asterisk L theta. And there's a good reason why it's G asterisk. It's because in the spatial domain, when you look at what that function actually means, it's just the inverse Fourier transform of, you know, our gk theta multiplied by this ramp function. So it's 0 at the origin and goes up linearly away. And so that is our new function in the spatial domain. And that new function is equivalent to our original GL theta we measured with the scanner, right? With our projections with the CT scanner, convolved with the inverse Fourier transform of the ramp. Okay. So we call that, say, GL theta convolved with this thing, right? Which is this. And we're going to now, with this formula, to finish off this inverse Fourier transform, we're going to add all of these up. For each theta value, we'll just add them up, right? Add these guys up. And so that is the new type of back projection we're doing. And that's called convolution back projection because we're back projecting these guys, which have this convolution before the back projection occurs. Okay. So graphically, we can, I think that battery died. Yes, it did. Here. Pausing for a technical change here. We got to put a new microphone on. Okay, that one looks good. Thanks. So we can look at it in two spaces. We can look at it in the Fourier domain, and we can also look at it in the spatial domain. We're going to get to the same place, which is this convolution back projection. So why don't we start in the spatial domain? Here's GL theta, which we have measured, right, on the scanner for this value of theta, this particular value. We got this function GL theta. We convolve it with this thing, and that is the inverse Fourier transform of the ramp, and it looks like this. Right? So after doing that convolution, we get these G asterisk L theta, and we back project those to get to our image. Okay. We can look at it also in the Fourier domain. It's equivalent. We take the Fourier transform of GL theta. That's this capital G K theta, right? So we have one value of that at a specific theta. We multiply that. We don't convolve. We multiply by the ramp function, right? The reason we multiply is the convolution theorem, right? Convolution in space is equivalent to multiplication in the Fourier space. So we multiply by the ramp, and all that does is it weights our data and then truncates the data, right? That's it. And then we take the inverse Fourier transform of that finite data now, and that gives us the estimate of the back projection. Yeah?
Sure, it's a smart thing to do abruptly truncating the data like that.
That is it's a terrible thing to do. Okay. Right? It's a really bad idea. But if it's noise-free data and everything's perfect on your scanner, that is the way you get the actual image back. The true image is this transformation. Okay, so if everything's noise-free and you have very, like say that, what was it? The phantom, the head phantom. It just dropped out of my head. I've only known that for 30 years. But anyway, that thing has an absolute perfect known image, right? You can just write down the equation of that image. To get that back, you need to do this, right?
So the weighting that you would get for doing that cutoff is less of an issue than simply resolving the issue.
Right, right. So you deal with the ringing, right? You can deal with the ringing if you set the whole thing up absolutely perfectly in the discrete space. Okay. Now, if it's this is where it gets tricky. If it's not set up perfectly, if your data is like offset a little bit from the optimal discrete sampling, then you will see ridiculous like Gibbs ringing off edges, and we'll see some examples of that. So yeah, it gives you the analytically correct image, but as we'll see, the filters like this come with problems. Yeah.
So one, what, pick A, does that doesn't make it, does that mean the absolute value of K, or is that just the way to represent those functions?
Yeah, it's the absolute value of K.
K a function?
Yeah, well, it basically, the function that we're doing is in the two-dimensional space, it will be 0 at the origin, and it will go up linearly in any direction from the origin, right? So it truly is the absolute value of K, which is the distance from the origin, gives you a circle all at the same height, right, around the origin. Yeah. No, it came up right here. We just derived why you need that filter, right? So it in fact is, because we're sampling the data in polar coordinates, and we have a high dense set of data at the origin and lower density as we go out, it has to be weighted like this in order to get the right numbers, right? And not blur all the edges, right? And so yeah, I mean, this is called the Romlock filter because the two guys that came up with it, well, we'll see their names. I can't pronounce their entire name because it's so long. But you know, that's theoretically what it should be. Practically, it rarely is this. Okay, and we'll see why. Because this is truncated, so in a sense, there's an additional filter here, which is like, I got to stop this madness. I'm going to truncate it, as opposed to amplifying more and more and more of this high frequency stuff, right? So anyway, so let's take a look at what this does to our. This is the fascinating part, really. So here's a projection of an ellipse at a specific angle. So theta here, it looks like a variable, but it's fixed, right? For each of these. So I have L is this direction on my detector. These are the values I get for the projection through the ellipse, right? For a specific L, this would change as I change theta. When I look at what the related G asterisk or G star L theta is, this is what it looks like. So this is post this convolution. So I take this, convolve it with this. Take this, convolve it with that sync looking function. It's not a sync, but looks like that. I get this. So few things can be noticed right off the bat, right? One, this, if we back project this thing, it's never going to give you an ellipse with a constant value in the middle, right? It can't. It has, these humps, right? So it's always going to have a hump in the middle, right? As you back project that thing. This one, on the other hand, has a nice flat top and says, oh, it's flat along this way. And also these edges that smoothly fade away, this goes negative around those edges. And it says we've got to suppress, these values that are coming off the edge. And so this is what it looks like in one direction, and that's what its projection back into the space looks like. This, it's constant all in here, and then it has these negative edges, which we'll see are going to like sharpen up the walls, right? And that's what it looks like with 3 of them. Here's going back to our example when we looked at just naive back projection. We had this phantom, and then we had these values for GL theta. And this is our sinogram, remember? And this is the L direction, theta direction. That's what all the GL thetas look like. Back project those, we got that fuzzy view. Here's what that function looks like. This is what it looks like after you do the convolution, right? With the inverse Fourier transform of the ramp, looks like this. And so when you plot this line and this line, that's what they look like. So this one is all positive. This one we know integrates basically to 0, right? Because we have multiplied in the Fourier domain, we multiplied away the DC term. It's 0 at, k x equals 0 or k equals 0. So there's no DC term. So the DC term would be whatever the integral is under this thing, right? So now we've got this plus and minus function, right? And we project these back, right? And lo and behold, after, projecting back more and more views, we get back our original function instead of something that has blobs here with, large foggy edges. Okay. So this, here you go. It's called a Rom lock filter because those of us who are incapable of remembering what this guy's name was, but we can't remember Rom and lock. It, is the simplest and analytical solution to this thing, other than the fact that, you've got to decide where you're going to truncate it. Right? It makes life a little better, and images a little smoother, right? Let's say it that way. If instead of having this abrupt change right here and this huge amplification of your highest frequencies, you run it off so that it maybe has a derivative of 0 at that peak, right here. Right, so you could put in here a cosine part of a cosine function so that it ran up and went to 0. And so the thing that you convolve at that point, you convolve GL theta with, Romlock looks like this. This is the cosine, right? So it has smaller edges and it's a little bit wider here, right? You can also, there's a Shep-Logan filter. You can just look this up online, what the actual functional form is. Here's a functional form. It's the ramp, but modulated by a sinc function. And then a cosine 2 is, it goes through a full cycle of a cosine. So it goes down to 0 out here. That's very aggressive, right? You're saying your high frequencies, I'm just going to make sure that it's at 0 by the time I cut off my window. And then a Hamming looks like this, and a Hanning is maybe the strongest, which is a cosine function that actually not only goes to 0 out here, but its derivative goes to 0 out there. So you've multiplied it by cos squared or something. And then when you look at the function that you run the convolution with, it looks like this. So it's got one main sine lobe, and it's a lot thicker, right? It's wider. So you're welcome to try any of these, in that simulation that we had there for those pictures, and see what the various pictures look like. I think most of these filters themselves, these filter kernels, well, this is the filter kernel that's historically been run on an array processor on a CT imaging machine. They're well guarded secrets, right, for each vendor, right? They feel that it's very important for them to use this particular filter on their machine, and they won't tell you what it is, right? So you have to go to all this trouble to go and measure the damn thing, right? You just do phantom experiments and average it up enough so that you just look and you see what the point spread function is. I don't know why they won't do it, but anyway, I think early on there was some leap in technology that someone made that way, and so historically they just don't let these things out the door. But for the most part, when you go through a set of filters, and then when you're reconstructing a CT image on the scanner, you usually have a choice of about 6 filters, right? All the way from what's called a bone filter, in which it's essentially a Romlock, right? So it's very noisy, but the edges are really sharp. And if you're imaging bone, you're way up above the noise floor and everything, so it doesn't matter that much. But when you're imaging soft tissue, most radiologists like a much smoother looking space than is provided by the Romlock filter. And so normally you're using a Hanning or something like that, right? And for good reason. I mean, the images just look a lot better. Like if you use the Romlock filter, they truly look extremely noisy, right? And so here's a rectangle with a Romlock filter. Here it is with the Hanning filter, right? And this is the noise-free data. And so you don't also see the relative noise level. Here is actual data from a scanner reconstructed with the Romlock filter here. And I think what they call the standard filter. They don't tell you what it is. It's called standard, right? And so, you know, it really smooths. See all this. If you took the root mean square deviation of these pixels to estimate the sort of random noise value, it's much smaller here. So the signal to noise of this object is much higher here than it is here. And also, as you alluded to, things didn't go well at these edges. They just didn't fit right. You know, they're sort of halfway between pixels or something, and it generates these enormous ringing artifacts, right, off those edges. And that's from the abrupt truncation of the data. Okay, so that's, and then this is what the background looks like. So you have background noise here, higher background noise, and more ringing out into the periphery. So here's some of the discrete convolution kernels that get used. You know, there's 10 points in these ones. So you take your raw data that's just coming straight from your, you know, scanner detector, and do a discrete convolution with this before you back project. Okay? And it's very fast. So CT reconstruction for a long time has been very fast because it's this simple process of just convolve and back project, and you can build a ray processor to do that easily. And they built special ones. So here's what a rectangle looks like after passing through the convolution, the discrete convolution of those different kernels. And you can see all of them have a relative amount of the same effect, just that this one has sort of a broader transition zone than this one. Right? They all look like Batman. Oh. Okay, so any questions on that? We're gonna keep going here then. Yeah, we're at 49. Okay. We've kind of run behind, but anyway, here's some other, I just put them in the slides for you, some other really good books. This is a great book. It's highly technical, but if you're going to do CT, you should read this book. And this is a classic. So there's, as I told you, there's about between 200 and 400 people on the planet who actually know how to do CT really well. And they all learned from this book, right? Because most of them are pretty old. So it's a classic book. So again, we look at, you know, the principle here is when we take the Fourier transform of our projection, we get this sampling. We could put that sampling on top of a Cartesian grid, and then for each point on this Cartesian grid, estimate the value at the Cartesian grid from the surrounding points, right? And this gives you an idea that, well, if I'm estimating a point down here, I'm going to have many, many values around me. So I'm going to have a weighting on those values, that like 1/16 or something, you know, because I've got so many points here. Whereas when I get out to here, that number drops precipitously, right? There's just the density of points drops out there, and it goes as K, right? That's why we have that weighting factor. So I think we've done this successfully, right? Went through that, did this example. Oh, okay, so let's do this. convolution back projection, right? These are the simple back projections, and this is the object that results from those projections, right? And then when you do that convolution before you back project the data, this is what the data looks like here. So it's more complex, but as you can see, it will essentially add up when it's all done to the actual object, right? And so the edges have high fidelity. So we've looked at that. Okay, so artifacts. One of the issues about doing this filtration is that while we get our projection, take the convolution to get here, we get a nice flat top and these negative side lobes that are going to keep the edges sharp. If I have a small variability on my raw data, right? So in this case, there's 3 channels like at a particular view angle that popped off some noise such that their value is 10% in error from the true value. Okay, and so this isn't a true noise simulation. It's just like, let's look what happens if, say, 3 pixels are kind of noisy on our projections. After you do the convolution, that gets really amplified in its effect, because remember that convolution is proportional to it, sort of the derivative of these things. And so in the back projections, that view that had the little noise spikes that occurred looks like this, and this is what your picture looks like. So you get this very unstable situation where if you have noise spikes, they are going to show up as these streaks in your image. Okay. If there's again, along this direction, a set, for whatever reason, there's a set of pixels that give you this 10% change at 45 degrees. You look at the filtered back projection of that view, and it basically looks like a very dark streak through the image. So any kind of instability in this signal gets amplified by this convolution process, and you get these streaks. If you have raw data such that one of your channels, right, has a 1% error, however, it's constant. It's like for every view, it's giving you 1% higher than it should, right? Its gain for whatever reason is like up 1% for those around it. This is what the filtered projection looks like. And it's, you can see there's a little blip there, but then when you back project it, this is what it looks like. And this is one of the most common things you see in a CT image when you get down to really low counts, like low dose. You start seeing these differences in the gains of the detectors, and these ring artifacts show up. Okay. So if you see these ring artifacts in say you get a CT and it's your dad's CT or whatever, your mom, you look at it and you see these ring artifacts, they either did a really low dose scan or it was a really crappy scanner, right? So you gotta work that out for yourself. But normally these pop up if a detector goes bad or whatever, they pop up and it's detected by the scanner itself, like in its sort of calibrating step, and it'll call the GE tech to come out. So in the book Prints and Links, Jerry Prince writes down a few equations. One is for the basic elements of determining what the spatial resolution is proportional to. And so here's the equation that we have to get our function, to invert our function. And this is the Fourier transform in polar coordinates of our function. And we have the K term, or in this, I don't know why he uses these letters, but the K term here, which is the ramp component. We also have that windowing function, and that's where do you cut that ramp off? So we saw the ramp go up and then it went down to 0 like that. So the width of that window is also something that's affecting what your resolution is going to be. And we also saw that we can make those things quite sophisticated and smooth, right? So we can, instead of having just a rectangle and cutting off, the ramp will have a ramp that rolls off much more smoothly. And so that's this windowing function. That's going to be probably the primary thing that determines the spatial resolution on your final pictures. And then there's the detector area blur. So remember, we have a set of, say, 1,000 detectors. So they have a finite width in space, right? And it's usually about 1 millimeter. Each detector is 1 millimeter, and they're stacked as close as they can together. So obviously, you know, if that thing is broader, our spatial resolution goes down, right? If the thing is a narrower and narrower detector, we can see a narrower and narrower space. We're sampling at a higher frequency in that theta direction. Our spatial resolution goes up. However, the number of photons per unit time for the same dose drops, like for each detector. So yeah, there's a balance, and there's also a balance in cost of just making that many detectors and that many individual receivers and amplifiers, etc. So those are the primary components. Oh, there is one missing out of this analysis. He does it in the book, but under X-ray imaging, not CT. And that's the X-ray spot size. So it also depends on how large is the rectangle from which the X-rays are coming, like from the tube. So they don't come from an infinitesimal spot. They come from a rectangle on the target. And so you can imagine that if I have a dot and I image the dot and I say, what does the dot look like from X-rays in the top corner of my rectangle? The dot's displaced in one direction. What does the image look like from the X-rays in the other corner of my rectangle? It's displaced this way. So there's a spreading, a convolution, as it were, of the sources, right? And the way this is usually simulated, when if you're writing a simulation of a CT scanner, you will just take the rectangle that is your source and you will divide it up into sourcelets. So you'll have 16 different sources, make 16 different pictures and add them up. And that's how you simulate that, right? And so that's the other thing that will cause blurring, is the spot size. And so when we do the experiment, this is going right back to the first lecture, we put in a very small metallic bead that's smaller than any voxel in our image and image it, and the image comes out, and this includes all of those factors, right? The point spread function that we create, it includes all of those factors. And you can quantify the resolution, as we said before, with this point spread function. And normally the way that's done is it's in millimeters, and you just go to the half height of this point spread function, measure the distance across it, and that's the full width at half max of the point spread function. So that's in millimeters, and it's a very easy thing to understand, right? It's just like, oh, my point spread function is 1.2 millimeters is the full width at half max. Most CT scanners, it's around 1 millimeter, right? Somewhere in that order. It's not 10 and it's not 0.1, it's around 1. And as we saw before, you can also quantify it with the modulation transfer function, if you like to think in frequency space, which is cycles per millimeter or cycles per centimeter, and it rolls off at the higher frequencies. And just reviewing how we looked at that before, here we're seeing as the frequency of the bar pattern gets higher in cycles per millimeter, you can see that eventually the contrast between the highest and lowest value in that pattern decreases, right? And that's the relative amount of decrease is shown in the MTF. Phantoms are designed such that you can just put it in and visually look at the phantom, at the output image, and measure what is the highest spatial frequency available, right? So here we have, you can see as we go around this arc, interestingly, the arc is at the same radius, right? It's not, we can't put all of these things at the center of the scanner, so they go along, but at the same radius. And the cycles per centimeter goes higher as we move ourselves along here. And this is just pulled out of a paper where these folks claim that with their filtered back projection or convolution back projection, plus their new twist to that, they can get basically higher resolution, judging by the contrast here versus here. So that's what they were doing here. And so these phantoms are available. And in most CT clinics, you have these and you just measure the image. All right, we have 2 minutes. This is, this is a kind of an interesting example. This is a heart in a jar. And this is a coronary artery of that heart with basically the lumen of the artery is this gray stuff, and then this is a piece of calcium. And so this is a high resolution picture of that heart in a jar. And the reason I'm showing it to you is because you can put it on the clinical scanner, and this is that object measured with a small spot size, with the X-ray source set to small spot size. There's usually 3 settings: small, medium, and large. And they go with the size of the patient. So if you've got a really small patient, you can usually get enough X-rays with a small spot size. If you've got a big patient, you need more X-rays, so you go to a bigger spot size. And here is the image on the small spot size. And we set the MA such that if we just change the MA by 1, it flips to the other spot size. So the MA is essentially equivalent here, the number of X-rays, but it flipped to the larger spot size here, and you can see the reduction basically in spatial resolution here. I don't know if I zoom in on it. Yeah. So this is with the small spot size. You get pretty well a central pixel that's bright, and then here it gets blurred out. Not a huge effect, not a game changer, right, for changing the resolution, but it's there. It's a measurable effect, right? Oh, this is, yeah. So we also imaged this heart in a jar on my colleague's benchtop CT system. So he built this system. It's pretty nice. And you just rotate the heart in a jar here, and you can see the difference. So this is on his system. This is the vessel wall, piece of calcium, the lumen of the vessel, right? And then when you go onto the clinical scanner, measure exactly the same thing. This is what it looks like. This is the highest resolution picture you can get on the clinical scanner, right? So, that's what it looks like when you have, high resolution features underneath and here. Now, what determines what is sufficient resolution is completely task specific, right? So if you're just trying to find nodules in the lung, you don't need super high resolution, right? If you're trying to find tiny little pieces of calcium, or you're measuring very, very small morphological features in the inner ear or something like that, then you want a higher resolution. And here's a difference between 2 filter kernels. Remember, the bone filter is the Romlock filter. Basically, it's the ramp filter. And the standard recon filter, I'm going to say it's like a Hanning filter. We don't know what it is, but it's something like that, right? And changes the background noise extensively, changes the peak value of the signal. So this peak goes up, right? Because the this signal that we've got here came out of a phantom designed for resolution, and it is a 50 micron tungsten wire, right? So it's running through the entire slice. It's only 50 microns in diameter, so it's much smaller than any pixel in the scanner. And we get a much brighter value here with the bone filter, right, than we do here. And when you draw the plot between, here's the standard filter, here's the bone filter, and we look at what it looks like on the standard, we get up to 500. On the bone, we get up to well over 1,000, like 1,200 Hounsfield units, right? So you could say it's more accurately determining the amplitude and the actual mu value of what's in that voxel, right? Than this one. This one is obviously wider than this. However, you look at the noise in the background here, and it's pretty darn high, right? So the signal to noise here is probably higher than it is here. So if detection is your goal, then you probably want to work in the signal to noise space, right here. And if you're detecting something that is bright and isolated, then it kind of doesn't matter if it spreads out, right? Because all you have to do is detect that it's there. You can take basically the center of mass of that blob and say, if that object was infinitesimally small, I predict it's here at the center of mass of the blob. And you're going to be right, right? So that's called super resolution. And in microscopy done in lit live cells and things like that now with fluoroscopy or fluorescence, they usually set, in some of these super resolution techniques, they set the rate of emission of signal such that they get individual fluorescent events, right? So then you can stack them in time and you can get this blob, and you know, oh, this is exactly where that thing is, and it didn't interfere with the stuff around it. If you get a lot of signals coming in simultaneously, right, they're all going to mix together and you can't see it. But anyway, that's super resolution. A rule of thumb, not perfect, but a good rule of thumb is if you have a cascade of events that are happening to your signal and each one has a point spread function associated with it, then to get the total point spread function of that whole cascade, you can just use this simple formula. If I have n of these events on my signal, you just take the full width at half max of each, square it, take the sum of the squares, and that's your new full width at half max, or your total for the whole thing. Okay. I don't know why this is in here. I think we'll, what time are we at? We're at 9, okay. This is just a review of signal to noise. We've already done this, right? We did this, I think, back in image quality, where you look at the background signal and the root mean square deviation on the background, the signal of your object and the root mean square deviation in here, and use that to determine the contrast to noise function as to whether or not you can detect it. And you know, that basically you assume in most of CT, if you're going to measure this contrast to noise function, that you assume that these two sigmas are roughly the same, that the signals are close enough together that these are roughly the same. And in the book, there's a pretty nice description in the book in this section, determining what actually changes the noise level on a CT scan. Like how is it affected by, say, number of projections? How is it affected by the width of the detector, etc. And so you know, he basically looks at it in a discrete way and says, here's our mean number of photons detected at any point divided by the you know, incident number, and he's going to work out what the variance is on the estimate of mu at a point as a function of CT imaging parameters, okay? And so he writes down, first, this is essentially the, inversion, the convolution back projection of our data, but in discrete form. And so we've got the number of views, which is J. So we've got a set of G values for a set of angles. We have inside each one of these views, we've got so we've got N detectors, and they're separated by T is the width, the separation width of the detectors. And then this is essentially the sampling down a line. And to get down to the brass tacks of this thing, or the results of this thing, if we assume, right, that all of our NIJs are about the same, right, if they, in the sense that we're not working with really, really low counts in one area and really, really high counts in another, but they're all around the same. You can say that the sigma squared of your mu estimate is proportional to these parameters. So let's look at the simple ones first. So M, right, is the number of angles over which we measure, right? So if I take 90 views and I get a picture and I look at my variance of my estimates of mu, and then I take 180 views and I look at my variance, it will be a factor of 2 lower. The variance will. Okay, so the noise went down by a factor of 2. So it's linearly proportional, inverse linear proportional to the number of angles. So more angles means lower artifacts for one thing, but it also means the signal to noise is going to get better because the variance is going down. It's just like averaging, right? This is the one that's interesting. This is basically the width of the convolution filter in Fourier space, right? So as that filter goes out to higher and higher levels, such that the cutoff is at higher and higher frequencies, the variance goes up as the cube of that highest frequency. Okay, and you can think of this, we're calculating the power. If I look at Fourier space and I have my Fourier transform of the object, say I have infinite high spatial frequency, or I got a lot of spatial frequency there, multiply it by the ramp function, so I get this object in Fourier space that is going up linearly as I move away from the origin, and the power that I integrate in there basically goes up as the cube of the size of that thing. So as my width goes up, the integral of the whole thing goes up as the cube for mu squared. So this is what basically kills you with the Ramlock filter, right? Is the fact that you give this remarkable weighting to high frequencies such that the noise gets amplified extraordinarily. And so even though your mu value may be more accurate and you may be better localized as you're going to higher and higher frequencies, the background noise is catching up to you, right? And so your signal to noise is going down because of this term, right? This term is essentially the number of detectors that we have along the L direction, right? So if I have more detectors of the same width, I'm going to get a lower variance, right? So adding detectors of the same width, I just get a lower variance. Interestingly, if you change the width of the detectors and add twice as many, you get the same variance. So think of that. If I had 1,000 detectors and I say, I want a higher resolution picture, I'm going to do 2,000 detectors. right? So we cut those in half, right? So, I get a bigger N, but the T also changed and they cancel each other out. So essentially what it means is if I have a signal, we can do it the other way. If I have a signal and I've got 1,000 detectors and my signal to noise, my variance is too high, I can take each pair of detectors and just average them together, and I'll get a lower variance in my scan. I'll get a lower, resolution, but a lower variance. So I don't lose anything in terms of signal to noise by averaging those neighbors together. So essentially you can just do that until your signal to noise is a level that is acceptable. Now the resolution goes down as you're doing that. But what scanner manufacturers do actually is they test, they take a test region in a scan and say, well, what do you want your variance to be? And you actually type that in to the scanner. You say, I would like my noise factor to be noise factor 4, Mr. Sulu, right? And you put that in there. And then inside the reconstruction, they decide how wide that averaging is going to be, right? So that's another term. Okay, I think this we'll do, we got 2 minutes. This is called a contrast detail curve, so this curve here is called the contrast detail curve. I think it's unique to CT in that you have basically a detail axis such that you get smaller objects as you go to the left, and a contrast means they're brighter here than they are down here. And the curve tells you where does it cut off, where can you no longer determine that an object is there. And so for one acquisition here, I don't know what they've changed here. Oh, so this is just more noise was added to the signal. So the signal to noise basically goes down. The contrast detail curve moves this way, in that these objects that you could previously see over here, they are no longer there. And what does that mean? It means that if you do the statistics, you look at the mean value over that point and calculate it from instance to instance, right? You may as well flip a coin as to whether or not it's there, right? And you can see larger objects because you can average up all the pixels in a larger area. And so your visual system is pretty good at seeing that, and so is arithmetic, right? It can see the mean value there. As they get smaller, right, eventually you run out of statistics. You just don't have enough pixels to tell that there's something there versus the background. And that's often shown as this contrast detail curve. Not my favorite thing, but it's something that's unique to CT, and you should know that it exists. Okay. Okay, so